class, welcome back again for another lesson. Today we are going to look at a new chapter which is an alternating current, and we are going to look at three components of an alternating current, which is a resistor, capacitor and inductor. But for today's lesson we are going to just look at alternating current through a resistor. This is class Barrage, teaching for Physics Form 6 semester 2. Class, for our next lesson, which is the learning outcome, is to derive the expression for the current from V equals to V naught sine omega t. We also need to explain the phase differences between the current and the voltage for a pure resistor. Now, what does a pure resistor means? A pure resistor means in the circuit there is no capacitor, there is no inductor, just a resistor. So before we go for this, to learn about this learning outcome, we need to understand few things. Let's move on to the next slide. Electricity comes in two forms. One is alternating current and direct current, which is DC and AC. Both are essential to enable the functioning of our electronic systems. But do you know the difference between the two and what they apply to? Both AC and DC describe type of current flow in a circuit. In direct current, the electric current flows in one direction. In the AC, the electric current flows in change direction periodically. The direct current, the electron flows in one direction. The electron flows in one direction shows that the current flows also in one direction. In alternating current, the electron changes its direction periodically. That means the current is also changing direction periodically. In direct current, it's a linear electric current. Linear electric current means in one direction. It moves in a straight line. That means if you look at this graph, the line is a straight line. The line is a straight line. So it's in a straight line. It is a current of a constant magnitude. But in alternating current, the current magnitude vary with time. So if you look at this diagram here, okay, here is T and you have a different time. Here is another T and here you have another different current. So this is current versus time graph. This is current versus time graph. So here the magnitude of the current is constant throughout the whole entire time. But here throughout the whole entire time the magnitude of the current varies with time. Okay, what is a phasor diagram, class? Very quick and very simple. A phasor diagram are the representative of a voltage current relationship in an AC circuit. Okay, so if you see the circle here, this is called as a phasor diagram. And the line you see here with an arrow, okay, this arrow here, this is called as a phasor. A phasor is a vector, okay, it's a vector capable of rotating about the origin omega, which is always in the anti-clockwise. Now, when the phasor is rotating, the arrow is rotating, it will generate a waveform. Okay, and the type of the waveform it generates, it depends on the initial position of the phasor. So if you see in this graph, the initial position here is here. So the type of generate is sine graph or sine function. Okay, so this is a phasor, this arrow is a phasor, this whole thing is called as a phasor diagram. So let's look at a few examples of a waveform. Look at the phasor diagram. Okay, a phasor is a vector of constant magnitude and rotating in an anti-clockwise. So it will rotate in this direction. Okay, omega, and then this will be omega. It will be rotating in this direction. This is called as a phasor diagram. This is called as a function waveform. Okay, so the first one we have this function waveform in current. Okay, this is current and this is time. Okay, so the sine function waveform, okay, we have I equals to I naught sine omega t. So if I want to draw the phasor for this function waveform, what I do is I look at the initial position. When I look at the initial position, then I connect it. Okay, connect it. It will come in this direction inside the phasor diagram. So I draw a phasor which is in this direction. Okay, so this is I equals to I naught sine omega t. Okay, then if I have a cosine function waveform, so what I do is that this is I equals to I naught cos omega t. I see at the initial position here. So when I look at the initial position, okay, I'm going to take something which is a bit darker here so that you can see the line. Okay, alright, so you look at that. So if I see here, okay, I connect it to the phasor diagram, the phasor will be in this direction. Okay, I. Okay, and then if I have a negative sine function waveform, negative I naught sine omega t, and if I draw it in the phasor diagram, I see the initial position here. Okay, and then I connect it, so it will be here in this direction. Okay, alright, so if I draw relating to it, not connect. It doesn't mean connect means connected, it's like relating to it. So in the phasor diagram, it will be in this direction. Okay, alright, then if I have a negative cosine function waveform is generated by a phasor. Okay, let's look at the initial position. The initial position is here. So if I relate it to the phasor diagram, it will look like it is in this direction. Okay, so this is I. Okay, so that is how. Now let's look at an example. If I have two magnitude rotating in an anti-clockwise direction with a constant angular velocity omega. So I have a two magnitude rotating in an anti-clockwise direction, which is omega. Okay, so this is the first one, which is Q equals to Q naught sine omega t. Okay, the first one. Alright, so if I draw the phasor diagram for this, okay, let me see here. Okay, so I see the initial position, I relate it to the phasor diagram. For Q in the phasor diagram, it will be in this direction. Okay, so it will be situated like this. So it is generated in the phasor diagram, so this will be Q. Okay, then if I look at the next waveform, which is this, so this one, say for example, is P equals to P naught cos omega t. Okay, then if I draw it in the phasor diagram, take it in the initial position, because a type of waveform is generated will depend on the initial position of the phasor. Okay, so it's like that. So this will be P. Okay, so that means we have a Q and P, and then we can say the difference between P and Q is pi over 2 radian. Okay, so we can say that phasor P and phasor Q rotating with the same angular velocity omega with a phase difference. So pi over 2 radian is called as phase difference. Okay, alright, it's pi over 2. So in this situation, what can we say is that we can also make another conclusion. Yeah, we can say that as this thing is rotating in this direction, we look at P is first. So we can say P is leading. Okay, P is leading. Phasor P is leading phasor Q. Because it's rotating in this direction, so phasor P is leading by phasor Q. Or we can say phasor Q is lagging. Is lagging phasor P. You want to add also can by pi over 2 radian. You also can say phasor P is leading phasor Q by pi over 2 radian. So pi over 2 radian is called as a phase difference. Is called as a what? Phase difference. Okay, so it's very important to see at the initial position. Alright, let's look at alternating current through a resistor. In your learning outcome, you need to derive the expression for the current from V equals to V naught sine omega t. Now here we have two diagrams here. This is the graph and this is the circuit. So if you see in this circuit, we have an alternating current or power supply, okay, alternating supply, which is fixed to a resistor. Okay, so this is called alternating current through a resistor. Okay, it's a pure resistor. Pure resistor means, that means in the circuit there is only a resistor. Okay, there is no inductor, there is no capacitor. Okay, so in this thing we are going to analyze about all the important details when there's an alternating current through a resistor. Now first thing we're going to look at is the voltage. Okay, so here the voltage will be V equals to V naught sine omega t. Voltage can be in sine and also can be in the function of cosine. But in your syllabus, it wants us to look at the function of sine. Okay, so if I draw a graph, the graph will look something, sketch a graph, the graph will look something like this. Okay, so this is V, this is T. So if I draw a sketch a graph, the graph will be in the function of sine, so it will look something like this. Okay, so this one is the peak voltage, which is V naught. It's called what? It's called as the peak voltage. Voltage can also be in the cosine function, but we are going to look only at the sine function. Okay, now a sinusoidal voltage source, okay, this is a sinusoidal voltage source, because this one is a source. Produce a voltage that varies as sine wave with time, as sine wave with time, not sine, sine wave with time. Point number 1. Okay, it can be expressed also. Now point number 2, it can be expressed with sine or cosine function, but we are going to look at only sine because this is what your syllabus says so. Okay, so now here we know that we have V naught here. V naught is called as the peak voltage. Okay, is called as the peak voltage. Peak voltage means it's the maximum voltage. Okay, is what is maximum voltage. Okay, then there are few things we should know, since it's in the function of like sine graph, which is a wave. Okay, so what we should know also, we should know two quantities which is very important. First is number 3, we should know period. Okay, period is capital T. What is period, class? Period is time taken for one complete oscillation. Time taken for one complete oscillation. Okay, alright, so we know T is equals to 1 over F. Okay, so if I draw in the graph, the one complete oscillation will be from here and then here and back here. So this will be period T. And we also know number 4, which I'm going to write here, is frequency. Okay, what is frequency? Frequency is F equals to 1 over T, alright, which is number of complete cycle per second. Number of complete cycle per second. Okay, and we know also another formula. Okay, these all are the formulas that you have studied in your circular motion. Omega is equals to 2 pi f. Okay, alright. Okay, so these are the things about we want to look at the voltage of an alternating current. Alright, at the voltage. Okay, let's look at the current that flows in the circuit. Now, the current in the resistor, okay, we know current. Now, let's talk about current now. Okay, current. Okay, this one is voltage. Okay, now the current in the resistor is, we know V is equals to IR. Okay, so I is equals to V over R, and V is V naught sine omega t, which I'm going to put it like this. Okay, V naught sine omega t, so I is equals to V naught sine omega t divided by R. Okay, so that will give you I is equals to I naught sine omega t. Why? Because I naught is equals to V naught over R. Okay, alright. So if I draw a graph of the function for current, I will get something like this. Okay, so it's a sine graph, right? So it will look like this. So this is I, this is T, and this one will be the peak current, I naught. I naught is called what? I naught is called as the peak current. Is called as the peak current, or is the maximum magnitude of the current, also known as the, as usual, maximum current. Okay, so that is about current. So one thing we can know here is, if we want to find the resistance, how do we find the resistance? We can find the resistance R equals to V naught over I naught. Okay, alright. So how do I get that? How do I get R equals to V naught over I naught? Okay, so if you look here, the resistance of a pure resistor can be expressed as V is equals to IR, R is equals to V over I, V is V naught sine omega t, and I is I naught sine omega t. So we get R is equals to V naught over I naught. We also can say it this way. Okay. Alright, so now we already analyzed the graph. Okay, in respect of its voltage, we talked about the voltage, and then we talked about the current, and then we talked about the resistance. So what we are going to do now is we are going for our next point, which we're going to compare with current and voltage. So we know about the voltage, current. Now let's compare between the current and the voltage. Okay, so the current, the graph will look something like this, and for voltage the graph will look something like this. So if I want to draw the equation, if I want to write down the equation, it will be I equals to I naught sine omega t, and this is voltage versus time, so this will be V equals to V naught sine omega t. Okay, so when we compare with these two graph, we can say I and V are in phase. I and V are in phase. Now what does it mean by I and V are in phase? Okay, so if you look at this, okay, now I naught, it reaches its peak at I naught at time, say I put here T1. Okay, at the same time, at time T1, voltage also reaches its peak. Okay, voltage also reaches its peak. Okay, so example, another example. Now, current reaches here at time T2. Okay, current is 0 at time T2. In the same time, okay, at T2, voltage also reaches 0. Okay, another example. One complete oscillation is, time taken is T. Okay, for the current. And the same goes to one complete oscillation. The voltage, the time taken is T also. So you realize that they do at the instant at the same time. Okay, that means I and V are in phase as both achieve their peak positive value and zero value at the same instant. Okay, so what I can say, both achieve their peak positive values and zero values at the same instance. That's why we say the word they are in phase at the same instance. Okay, alright, number 2, what can we talk when we compare between these two quantities? Okay, we can say I and V, their phase difference is 0. Their phase difference is what? Is 0. Okay, let's look at that. Let's draw a Phasor diagram. In order to know the phase difference, we have to draw a Phasor diagram. Okay, so I'm going to draw a Phasor diagram here. Okay, now let's look at the first one, which is the current. Okay, so current initial position is here. So if I draw in the Phasor diagram, the line will be here. The Phasor, not the line, the Phasor, I. Okay, alright. Then if you look at, okay, let me take another color pen. If I look at voltage, the initial position is also here. So when I draw a Phasor in the Phasor diagram, this will be V. So their phase difference is what? Is 0. Okay? Alright. So that's all, class. So for the first part, which we did was, we analyzed the alternating current through a resistor. We spoke about the voltage. We spoke about the current. Here you have to know how to derive the current. The learning outcome wants you to know how to derive the current. The expression for the current from V equals to V naught sine omega t. Then they ask you to explain the phase differences between the current and voltage for a pure resistor. So this is what I explained. Okay? Alright. Now our next learning outcome is to explain the concept of a RMS value of an alternating current and calculate the RMS value for only sinusoidal case, and to derive and use the formula of the power in an alternating current circuit which consists of only a pure resistor. Concept. Okay? Now, number 1. Mean value of the current over one complete cycle is equals to 0. Okay, why do we say that? Now let's look at this graph. Now this is one complete cycle, correct? One complete cycle. So during this one complete cycle, this first half is positive I. From here to here is positive I. Then the next one is negative I. From here to here is negative I. So the mean value will be the positive I plus negative I will be equals to 0. Okay? Alright. But what happens is, the reality is, okay, when alternating current flows in the resistor, heat is dissipated. Heat is what? Heat is dissipated from the resistor. Okay, so now I have an supply, voltage supply, alternate, fixed to a resistor. So when current flows into the resistor, heat is dissipated from the resistor. So that means the mean value of an AC cannot be the effective value of alternating current of an AC. Okay, so this one cannot be the effective value of an AC. So who is the effective value of an AC? Okay, let's look at this. When we look at current, okay, let's draw a current graph. This is I, this is T, so it's a function of sine. Okay, now there are 4 values of current. Okay, 4 values of current. The first thing we can know, the first value is I peak. Okay, I peak, number 1. Number 2, I at any time t. I at any time t. Okay, number 3 is I min. Number 4 is I IRMS. Okay, IRMS is called as root mean square. Is called as what? Root mean square. R means root, M means mean, S means square. Okay, so what is this? This is root mean square. So this is the 4 values of current. We got I at any time t, we got peak current, we got mean current, we got root mean square current. So out of all these four current, which is the effective value of an AC? I mean cannot be the effective value of the AC. I mean cannot. So which is the effective value of the AC? The effective value of the AC will be IRMS. Okay, point number 3, which I'm going to write here. The effective value of N, or of the current, in AC will be IRMS. Okay, alright, so this is one concept. Okay, now what does root mean square value says? Okay, now the RMS value, okay, now this is the definition. So let's look at your textbook. Okay, let's look at your textbook. Right, this is your textbook. Okay, the key word here, the mean value of the current does not represent the effective value of the AC. Number 1, point number 1. Okay, now here, another one more here, the mean value of the current is 0, point number 2, and it's not the effective value of an AC. Okay, point number 3, root mean square value of an AC is the effective value of the current, point number 3. Now what is the RMS value? The definition it is. The definition, the RMS value of an alternating current is the value of the direct current that dissipate heat at the same rate as the mean power dissipated when the AC flows in the resistor. This is very, very important. Okay, this is the definition for RMS value. It says the value of the direct current that dissipate heat at the same rate as the mean power dissipated when the AC flows in the resistor. So now I'm going to explain this point number 4. This, the definition of the RMS value of an alternating current is the value of the direct current, okay, which is IDC, okay, that dissipate heat at the same rate. Now what does it mean, dissipate heat at the same rate? That means E over T. E over T means it's power, correct? At the same rate as the mean power, okay, mean power dissipated when the AC flows in the resistor. So the RMS value of an alternating current, which is IRMS, is the value, okay, from the definition, IRMS is the value of the direct current, dissipate heat at the same rate, that means P, okay, as the mean power. As the what? The mean power. So this is what the definition is trying to tell us, okay, of the IRMS. Okay, so I'm going to draw a 2 circuit here. Okay, one is a DC circuit which is fixed to a resistor. Another one is a AC circuit which is fixed to a resistor. Okay, so this is a DC circuit, this is an AC circuit which is fixed to a resistor R. Okay, so the concept says if the power dissipated in the DC is P, the value of P is the same as the value of power dissipated from the AC, which is the same value as the mean power from the AC. That means if the P is, like, say example is 20 watt, the value of this 20 watt is the same as the value of the mean power which is dissipated from the AC, from the resistor of which is fixed to an AC. Okay, so that means the current that flows in the DC, which is IDC, is the same value as the current that flows in the AC, which is the current of the IRMS. Okay, alright, do you understand that? Okay, so P is equals to the power dissipated at the DC is the same as the mean power dissipated in the AC. Okay, alright, so the mean power of an AC, alright, so from here we will look up to this. Okay, one more. P is equals to, we're going to take I square R. We can also use V square over R, but we're going to look at I square R. Is equals to mean power. Mean power, if you look at the concept, which I'm going to teach you later, yeah, is half I naught square R. Okay, alright, so the power of an DC, I square R, is equals to the mean power of an AC, half I naught square R. Okay, alright, so here we will see I is equals to, I square is equals to half I naught square. Okay, and then I is equals to I naught square root of 2. Okay, I naught over square root of 2 is actually IRMS. Okay, I'm going to just put here DC, and here I'm going to put DC. Okay, so why? Because later you will look at the formula there. IRMS is equals to I naught square root of 2. What is I naught? I naught is actually peak current. Peak current. Okay, alright. Okay, in the same manner, if I want to talk about the voltage, also we can talk about the VRMS. Okay, I'm going to use another color pen, which is the blue pen. The VDC, the voltage of a direct current, is the same as the voltage of the VRMS of the AC. Okay, if the power dissipated at the DC is the same power as the mean power dissipated at the AC. Okay, so here if I look at this, P is equals to mean power. This is AC, this is DC. So P is V square over R, which I'm going to put VDC. Mean power is what? Half V naught square over R. Okay, alright. Okay, so from here I get what? V square DC equals to half V naught square, and then if I square root, then I get VDC equals to V naught square root of 2, where V naught square root of 2 is actually equals to VRMS. So VDC is equals to VRMS. Okay, if I talk in the aspect of voltage, this one is in the aspect of current. Okay, so I give you all an example here. Here, in a circuit, the alternating current of RMS value is 1 ampere. So that means it's trying to tell us that I RMS is 1 ampere. Passes through a resistor. So we have a alternating current. So I'm going to just draw like that. Passes through a resistor. Okay, this is 1 ampere, which is IRMS. In another circuit, a steady current. Steady current means it's in the DC circuit. Okay, because current is steady in the DC circuit. A current of magnitude I passes through an identical resistor. So this is the same resistor. If the two resistors dissipate heat at the same rate, what is the value of I? So this resistor is dissipating heat at the same rate. So the power in the AC is equals to the mean power. The power in the DC is equals to the mean power of an AC. Okay, so therefore we can say that I of a DC is equals to IRMS, and the I of a DC is what? Is I. IRMS is what? Is 1 ampere. So the answer will be B. Okay, at the next quantity, which is power. Okay, we look what? At power. Okay, first thing, power. Power dissipated from the resistor. Okay, we can use two formulas. Okay, one is P equals to I square R, and next is P is equals to V square over R. Okay, now we know from our learning from our lesson just now that I equals to I naught sine omega t, which I'm going to just write omega t. So therefore, if I substitute inside here, I get P equals to I naught sine omega t square R. Okay, and then same goes to here. I know V equals to V naught sine omega t, and then V is equals to power is equals to V square V naught sine omega t square over R. Okay, so if I substitute, if I square this, I'll get P equals to I naught square sine square omega t R. Okay, and then I bring here, I get I naught square R sine square omega t. Or if I use it in this formula, I get P equals to V naught square sine omega t square over R. Okay, so therefore, if I change this, P equals to P naught sine square omega t, where P naught is called as the peak power. P naught is called what? P naught is called as the peak power. So peak power P naught is equals to I naught square R. Okay, and then if I do it here, I said P equals to V naught square over R sine square omega t. Okay, so this V naught is peak power. Is what? Is peak power. So I can say this is peak power P naught. So I can get P naught is equals to V naught square R. Peak power. Okay, alright. Okay, so now we know the first thing is the peak power. So if I draw the graph, you will realize this is the line. This is the line which I'm going to focus on the line. Hold on here. Okay, this is the line for the graph of power, like this. Okay, where this is the peak power. Peak power. Okay, now the next one is we're going to look at mean power. Mean power is half of peak power. So if I use this formula in respect of I will get mean power is half I naught square R. If I use this, I will get mean power is half of peak power. So I get V naught square over 2R. Mean power. Okay. So if I draw in the graph, it will be here, half of peak power. So this is peak power, right? So half of it, this one will be what? This one will be mean power. Okay? Alright. Oops, this one is V naught square over R. Okay, sorry, this is over R. This is over R. Again, V naught square over R. This is V naught square over 2R. Okay, alright. Next concept here is from the explanation of RMS current, we know the mean power of AC is equals to power dissipated by IRMS in DC, direct current. Okay, so let's look at this. Mean power of an AC. Now let's draw a circuit of an AC. Okay, this is connected to a resistor. Okay, the current flows here is IAC. Okay, then the power dissipated is mean power, is equals to, this is resistor. Okay, so the current that flows inside here is IDC, and we know IDC is equals to IRMS, effective value RMS current in an AC. Okay, so here the power dissipated is P. So we can say the mean power, okay, mean power is what? Half I naught, okay, square R. So here this power is I square R. IDC we know equals to IRMS. So therefore we can say half I naught square R is equals to IRMS square R, and therefore we get what? IRMS square equals to half I naught square, and then we can get that IRMS is equals to I naught square root of 2. Same goes to voltage. Same goes to what? Same goes to voltage. So let's say for example, mean power, we want to look at voltage, right? So mean power half V naught square over R is equals to, in the DC is, power is V square over R. And the voltage, the voltage of a DC equals to VRMS of an AC. So half
V naught square over R is also equals to VRMS square over R. So therefore, what do we get? V naught square over, okay, I'm just going to do this. So VRMS equals to V naught over square root of 2. So we can get this also. A relationship between IRMS and VRMS. Okay? Alright, so that is all class. Clear the air about this, why I wrote like this. Okay? Okay, what I was meaning when I wrote this is the mean power of AC. Okay? The mean power of an AC. So I have an AC here. Okay, dissipated mean power. Okay, and dissipated by also the power dissipated by a DC. Okay, so the I here is I DC and here is I RMS. Correct? So what I'm trying to say is that the power dissipated by the DC, is I DC is equals to I DC is equals to what? IRMS. So that's why I wrote here power dissipated by IRMS. Okay, or I can say IDC. So if you see in your textbook, you will see it says here the mean power of an AC is power dissipated by direct current. Where power dissipated by direct current is IDC, and IDC is equals to IRMS. That's why they put here IRMS. Okay, so just to clear on that. Alright, so that's it.